and share screen. Desktop. Share. Can you see my screen?
Yes.
Okay, great. So today we're going to talk about a model called logistic regression, again, supervised learning. This is a very important model. It's our first step towards neural networks, right? Which is the essence of deep learning. Okay, so we're going to talk about the model first, and then we'll see what is the error measure for this model that we want to minimize. So how do we get the weights that minimizes the error measure? And then we'll see the learning algorithm that minimizes the error function. So linear models, we've looked at various linear models. One of them is the perceptron, another one is linear regression. And the linear models, they are linear in the weights. Yeah, so you multiply the weight by corresponding feature value, and you sum over all the features, and that gives you a signal. Yeah. We looked at linear classification, linear regression, and today we're going to look at logistic regression. It's also a linear model. Yeah. So it operates on the same principle. You have a set of weights, you multiply them by the feature values, and so on. Okay. So let's see the difference between the three. In linear classification, you have the hypothesis of a given input data point. It's just sign of that signal, of this signal. So we do summation from I equals 0 to D, Wi xi. That gives you the signal. You take the sign of the signal. If it's positive, you say +1. If it's negative, you say -1. Again, we're talking about binary classification. Okay. Sorry. Let me see the chat. Okay. Okay, good. Now, linear regression was to predict a real value. So now we're not classifying, yeah? So you just take the signal as is. You just do summation from I equals 0 to D, Wi xi. That gives you, a real value, and that's what you use as the hypothesis. In logistic regression, we take the signal, pass it through some nonlinearity theta. Yeah, so it's a nonlinear function. It's a function of S, and we'll see exactly what this function is. Yeah. Okay. So visually, the linear classification uses a hard threshold. So it takes a signal, which is weights multiplied by feature values, takes the signal and either make it -1 or +1. Yeah, so +1, -1. Okay, that's the hypothesis. In the case of linear regression, you take the signal and output it as is. So you're doing no thresholding at all. Finally, in logistic regression, it's something smooth. It's similar to the hard threshold, but it's smoother. Yeah. So it's a real value, and it's also a real value similar to the linear regression model. Yeah. So it's a real value, but it's bounded by upper bound and lower bound, and we'll see what these bounds are. Okay. So here's the formula for logistic regression. Yeah, the theta function, the nonlinearity that we pass the signal through. It's e to the power of s over 1 plus e to the power of s, where s is again the signal. Yeah, let's see how it looks like. So visually, it looks like this. It's bound between 0 and 1. It's a value between 0 and 1. If the signal is very negative, it's 0. If the signal is very positive, it's 1. And is equal to 0.5 when the signal is equal to 0. Yes, when the signal is equal to 0, it's 0.5 exactly. Yeah, we can verify this from the formula as well. If s is very negative, you have e to the power of minus negative, large negative value over 1 plus e to the power of negative value. that's basically a small value over 1 plus very small value. That's a very small value divided by 1. That's 0. Okay. 1 second. Let me see the chat. Limits, yes. Okay. Now, when S is very large, right? So positive infinity, you have e to the power of a very large value. So e to the power of infinity, that's a very large value, over 1 plus e to the power of a very large value. That's basically almost very large value. So large value, say almost the same large value in the denominator, they cancel each other and you get 1. And when S is equal to 0, I get e to the power of 0, which is 1, over 1 plus e to the power of 0, which is 1. That's 1 over half, and that's 0.5. Okay? So it has these properties, this logistic function that I pass the signal to. So as we said, it's a value between 0 and 1. If S is very positive, then theta of S will be 1. And if S is very negative, then theta of S will be equal to 0. It's a soft threshold as opposed to the hard threshold of linear classification. Yeah. So in the linear classification, I take the signal, and if it's positive, I give it +1. Otherwise, I make it -1. So if it's negative, it's -1. And this is a very hard threshold. This one is smooth. Yeah. So it squashes the values from negative infinity to positive infinity to the range of 0 and 1. So it's smooth, right? So it's similar to the linear, but it's not as not the direct value as the linear regression. Okay, so sigmoid, it's called sigmoid, this function, right? The logistic function theta, and it refers to a flattened out S as opposed to the sharp linear regression, yeah? To the line. Very sharp line, this is a smooth line, if you wish. Okay. Good. So it has a very nice interpretation as well. It has a probabilistic interpretation, and that's what we're going to build the model on. So the hypothesis h of x is equal to the theta of s, theta of the signal, is interpreted as the probability of the +1 class. So basically, let's say I have the weights. I've already figured out the weights. I have an input instance. It's not going to output +1 or -1. It's going to output the probability of the instance being +1. Okay. So let's see an example scenario. Yeah. So when is this useful? It can be used to apply for any classification problem, but some scenarios are more suitable for logistic regression than others. Yeah. But again, it can be applied to any classification problem. Yeah. So it's a general model. So let's say I'm predicting heart attacks. My input is cholesterol level, age of the patient, weight of the patient, and so on. Yeah, smoking or not, etc. Okay. Now, theta of S is going to be the probability of a heart attack. Okay. So, what is the probability of heart attack? So, I cannot predict, right, given a patient, right, that they will definitely have a heart attack. Yeah, but I can say there is a very high chance that they will have a heart attack based on cholesterol level, age, and weight. Of course, they might not have a heart attack. Yeah, so it makes sense in these scenarios that I'm predicting a probability rather than a +1 or a definite +1 or -1. Okay. So theta of S is the probability of a heart attack, and S itself is going to be something called a risk score. It's how much risk does a person have for getting a heart attack. Yeah. So the signal, which is summation from I = 0 to d wi xi, where xi is the features, is just a risk score. So if it's very positive, there's a very high chance, or the probability would be very high, close to 1, of a heart attack. If it's very negative, then the probability of a heart attack is very small, it's close to 0. Okay, because remember, theta of S squashes the values between 0 and 1. Very negative values are 0, very positive values are 1. Questions so far? Okay. Good. Is there any lagging or any issues with the connection, or you can hear me well?
No, all good, sir.
All good, all good.
Very
Very
good.
well.
Very good, very good. Okay. So let's see this probability interpretation. We'll continue with the probability interpretation. It's a genuine probability, meaning what? Meaning that you assume that your data set is generated through this probability, yeah? So we're given a data set, which happens to be, it's a classification, so it would be a set of data points, and their labels, +1 or -1. So there are no probabilities at all. Where does these probabilities come from? We assume that the data is generated according to some noisy target, yeah? So you're given, instead of estimating, right, +1 or the label, right, +1 or -1, you're estimating a probability of being +1 given X, yeah, or -1 given a particular data point X, yeah, and we'll assume that this is generated by a probability f of X, right? So the unknown target function is now a probability function, yeah. So it's f of X for y equal to +1, and obviously, right, if the probability of being +1 is f of X, then the probability of -1 is 1 minus f of X, yeah, because we have a binary situation here. Okay, so the random variable has two values, +1 and -1. Okay, so basically, right, this f of X is a function, the unknown target function, takes, right, the d features, the feature space, right, r to the power of d, and maps it to 0, the interval 0 and 1. Yeah, so basically a probability between 0 and 1. Okay. Now, what are we learning? We're learning a hypothesis, g of X, based on the training data, which is equal to theta W transpose X, because W transpose X is the signal, yeah, summation from I equals 0 to d W, right, times X, W I times XI. That's in vector form W transpose X. Okay, we pass it through the theta, the nonlinearity, the sigmoid function. That gives me a value between 0 and 1. This is going to be the probability of the +1, yeah, which is f of X. Yeah, so the approximation of f of X, the unknown thing, right, that generated that training data. So our goal is to do what? Is to find the weights, W, that give the best probability of generating the training data. So given a particular W, right, let's say I have multiple W's, an infinite number of W's, yeah? These are weights, real values, so it could be infinite. Now, which one out of all of them gives you the best, right, probability of generating the training data? In other words, yeah, that if I fix W, or I look at a particular W, I can see, right, is it very high for the +1 instances, so for the instances that have, label +1, is this theta W transpose of X giving me very high probability? And for, right, the ones that are -1, right, so an instance with label -1, is it giving me very low probability? So that 1 minus f of X is high, right? Or 1 minus theta W transpose X is high. Yeah, so basically I have a training set which has only instances in input space X and the labels +1 or -1. I want to find the weights that maximizes the probability of generating the training data. We'll see this in more details in a bit. Any questions about the interpretation? Okay, good. So just for now, right, we understand that we're looking at a probabilistic model. Yes. Okay, what f of X is? F of X is the probability, right? Assuming there is a probability that generates labels for a given point. So basically, you can have a point or a sample or an instance, and this instance, right, could have a label +1 with some probability, a label -1 with some probability. So this is what f of X is. It's that probability. Yeah. So yes, I observe the data and it has a particular label. Every point has a particular label. But the assumption is that this label could have could have been different, right? It's generated by some probability. Okay. All right. So the error measure. As we said, right, for each point x, y is generated by probability f of x, meaning that, right, what made this become +1 or -1 is dictated by the probability function f of x, right, which is unknown to us, but we want to estimate it from the training data. So we're going to measure an error based on the likelihood of getting the right y from x. Yeah, we have the x, we have the y's. Now we want to try to see, right, given a particular weight, what is the likelihood of getting the right labels, right, from x. Okay, so I have probability of y given x is originally f of x for y equal to +1, and 1 minus f of x for y equal to -1, where f of x is the unknown. Okay. So I'm gonna approximate f of x using some hypothesis h of x, which is dictated by some weight. Yeah. So I given a hypothesis h of x, which is theta of, right, w transpose x. So it's dictated by some weights. Yeah. This hypothesis approximates the f of x. I want to measure how good it approximates f of x based on the training data that I have. Okay. So I want to maximize the probability of y given x, yeah, using this hypothesis. So using these weights, what is the probability that if I look at a particular point or instance that I get +1? Yeah, does these weights give me very high probability of generating +1 for this instance? Yes or no, right? And I do this over all the instances that I have in the training set. So some weights might be really bad. Yeah, it gives you for the +1 instances very low probabilities, and for the negative instances very high probabilities. That's a terrible value. Yeah, so I shouldn't, or a terrible hypothesis. So I shouldn't really take this as my final hypothesis. Another hypothesis, right, based on some other weights, might give me very high probability. If I look at every positive instance, it gives me very high probability, right, of y being +1, and very low probability for y being -1. So that 1 minus h of x is equal to, is high. Yeah, so if h of x is low, then 1 minus h of x is going to be high. Okay. So computing the likelihood. Okay. So I have, right, again, right, I have my hypothesis h of x, which depends on the weights, is the probability py given x. Yeah, probability of being +1 or -1 given x. Okay. What is h of x? It's theta of s, right, the signal, which is theta of w transpose x. Yeah, so basically nothing but weighted sum of the weight times the features, and then passing this through the sigmoid function theta. Okay, that gives me a value between 0 and 1. Okay. So I have here a branched condition. I want to, right, put this into one line. So let's see how to do this. Sorry. So one observation is that py of x is equal to theta y of s, right? Since theta of minus s is equal to 1 minus theta of s. So let's see what this means. I have py of x is equal to h of x when y is equal to +1, where h of x is equal to theta of s, right? So what is theta of s? Let me open the notepad for a second, or what is it called? More annotate, maybe? No, not annotate. See. Okay. 1 second. Yeah, new share. Whiteboard. Okay. So I have theta of S. Oops. Why is it doing this? Resume share. Sorry, guys. You can see the whiteboard, right?
Yes.
Okay. So theta of S is equal to what is it equal to? E of S one second. Yeah, here it is. E of S over 1 plus E of S. Okay, so let's see what happens, right? I want to show that theta of the theta of minus S is equal to 1 minus theta of S, right? So what is theta of minus S?
E to the power minus S over 1 plus e to the power minus S.
Exactly. Right. E to the power of minus S over 1 plus E to the power minus S. Okay. I can multiply both sides by E to the power of S over E to the power of S. So I didn't multiply by anything. Okay. That gives me 1 over E to the power of S plus 1. Agreed? Yes? So I just, E to the power of minus S times E to the power of S is E to the power of 0. That's 1. And then down there is E to the power of S plus 1. Okay. Now 1 minus...
Which is 1 minus theta of S, right?
1 minus theta of S is going to be equal to... Sorry, the annotation is really ugly, but I'm using the mouse pad. So it's going to be 1 minus E of S over 1 plus E of S. You take common denominator, you get 1 plus E of S here. And you get here 1 plus E of S minus 1 minus E of S, which is 1. So I get this is the same as this. Okay? So basically, theta of S is equal to 1 minus theta of S. Theta of minus S, sorry, this is theta of minus S. Yeah? Theta of minus S is equal to 1 minus theta of S. Okay. So going back to the slides. 1 second, resume share. Okay, can you see the slides?
No.
Okay, so let me start sharing again. Where is it? Here, right? Share screen. Desktop share. Okay. Now?
Yes.
Okay, guys. So I had probability of y given x is equal to h of x for y equal to +1 and 1 minus h of x for y equal to -1. And I'm claiming that this is the same as probability of y. The probability of y given x is equal to theta y of s. Okay, so let's see how. When y is equal to +1, I get the probability of y given x is equal to theta of s, which is h of x. Okay, when y is equal to -1, I get the probability of y given x is equal to theta of -s, because y is -1. And since theta of -s is equal to 1 minus theta of s, I get that probability of y given x is equal to 1 minus h of x. Okay? So I can write this probability of y given x, as simply theta of y s. Okay? Good.
So can you repeat that? You lagged a bit.
Yeah, okay. So again, right? I want to say probability of y given x, just one line. So I said this is equal to theta y s. So why is this the case? When y is +1, I get simply that p y given x is equal to theta of s, right? Because y is +1. Where is theta of s? It's h of x. Okay? Now let's see the case when y is equal to -1. I get probability y given x. I ideally want it to be 1 minus h of x, right? And I'm saying that's theta of ys. Theta of ys is theta of minus s, and theta of minus s is equal to 1 minus theta of s. Whereas theta of s, it's h of x. So py of x is equal to 1 minus h of x when y is negative, and equal to h of x when y is positive. Clear now?
Yes.
Okay, good. Worth S, it's again W transpose times X. It's just the signal, right? The weights times the feature values. So that's the probability Y given X. Yeah? For every point X, to get the probability of Y given X, what is the probability of +1 given X? It just basically you take the theta, multiply the value of Y times the weights times the feature vector, you get a value between 0 and 1 that tells you what is the probability of y of +1 given x, and you can get right or the -1 given x depending on the label of x. Yeah. Okay. Now the likelihood, this is the likelihood of a particular point, one given point. Yeah. What is the likelihood of the whole data set? So I'm given again as before n data points and their labels +1 or -1. Yeah. So basically, the likelihood of the whole data set is the product over all the points. I assume the points are all independent, so withdrawn independently. And so it's the product of P of y, the likelihood of a single point, yn given xn. Yeah. So this is the product from n equal 1 to n, theta of yn w transpose xn. Why did we do the product? Because we want to do the likelihood over the whole data set. We have the likelihood for one data point. We want to say what is, given these weights, W, or a particular hypothesis, what is the likelihood of this hypothesis or this data set, this weight, generating the whole data set, not a single point. Yeah. So how do I do this? It's the probability of it generating the first point, times the probability of it generating the second point, times the probability of it generating the third point, and so on. So that gives me the likelihood over the whole data set, right? Because the points are independent from each other, or assume that they are independent from each other. Okay, great. So what is the unknown here? It's the W. Yeah, this is the W that I want to get. We still haven't said how do I get this W. Yeah, but some intuition here. Again, we're given a data set which has some points, some tweets, and then +1 and -1, or some patient informations, and this person got a heart attack, this person did not get a heart attack. That's what you get as a data. Yeah, you don't get probabilities, you get just labeled data with +1 or -1. Okay. Now, given particular weights, so some W, I want to see what is the likelihood again of this W generating the data set. So over the whole data set, yeah. So ideally, I should get, if its weights are good, I should get this theta yn W transpose xn to be very high, right, close to 1 for all the positive instances, and very small or close to 0 for all the negative instances. Yeah, that's what makes this W good. A poor W would give you, right, that, right, basically the probability or theta yn W transpose xn is very high for negative instances, where yn is equal to -1, and very low for positive instances. Yeah? So that's a terrible W. Okay, so we want the W that maximizes this likelihood, right? For the positive instances, you get this quantity to be close to 1, and for negative instances, you get this quantity to be -1. And you do the product, this would give you, right, an estimation over the how good it's doing over the whole data set. Okay. Questions? Good. So I want to maximize the likelihood. So summation is a product from n equal 1 to n theta of yn W transpose xn. So where maximize it with respect to what? With respect to the W, the weights. Yn are known, xn are known. I want to just maximize with respect to W. So I want to find the W that maximizes this quantity. We usually don't do maximization in machine learning. We do minimization of an error. Yeah, this is what we have been doing. So mean squared error, we minimize it. This classification error, when we did perceptron, we minimize it. So we ideally want to minimize an error. So we'll take this quantity and I'll turn it into an error function. So how do we do this? First of all, I'm going to take the len. So maximizing this quantity is similar to maximizing the len. Why? Because this is a positive value and the len is monotone. Yeah. So basically, I get that doing the len would not change anything. It's just right, the same W that maximizes without the len would be the one that maximizes with the len. Why am I doing the len? Because I have a product here. Yeah? So I want to get rid of this product. Yeah? So it becomes closer to what we've seen as error functions. So summation and instead of product, right? We did this when we're doing all errors measures that we looked at, it was always a summation over the data points. Yeah. In fact, I'm going to do something else, which is averaging. Yeah. So I divide by 1 over n. Again, right, this doesn't change the objective function or the optimization problem, right? I'm just multiplying by a scale. So maximizing this quantity, the same as maximizing just the product without the 1 over n. Yeah. Len of the product without the 1 over n. Okay, so I want to find the W that maximizes this quantity. Why 1 over n? So that it becomes an average, yeah? So an average error. Okay, now instead of maximizing, I'm gonna minimize the negative of this quantity. Yeah, so this is the objective function or the error function for the logistic regression. Yeah, so minimize -1 over n len product from n equal 1 to n theta yn W transpose xn. Okay, let's just simplify this formula a little bit. It'll become really clean and nice. So what can I do? I can take the len, right? The len of the product becomes some summation of the len of the individual values. Yeah, so I get -1 over n summation from n equal 1 len theta yn W transpose xn. And then I put the negative inside, so that gives me 1 over theta yn W transpose xn. So minimize 1 over n sigma from n equal 1 to n len 1 over theta yn W transpose xn. Yeah, you can assume that this is right. So the -1 is because you have this can be written as theta yn w transpose xn to the power of -1, the -1 goes outside. Yeah. And again, len over product is summation over the individual lens. Okay, so far so good? Good. Now, theta of s is 1 over 1 plus e to the power of -s. It's e to the power of s over 1 plus e to the power of s. If you multiply both sides by e, like not both sides, right? The numerator and the denominator by e to the power of -s, you get this form. 1 over 1 plus e to the power of -s. Okay, so it's the same thing as we had it before. Okay. Why is this nice? Because now I know I have 1 over, right? So I get 1 over 1 plus e to the power of -s. So theta is 1 over, so this quantity is 1 over 1 plus e to the power of -s, which is equal to 1 plus e to the power of -s. You see it? It's 1 over 1 plus e to the power of -s. The denominator appears in the denominator, and so it becomes len 1 plus e to the power of -s. Okay, so the error function that logistic regression minimizes is basically this average of the following quantity, right? Len 1 plus e to the power of -n yn w transpose xn. It's e to the power 1 plus e to the power of -s. I know that e to the power of -s is e to the power of -yn w transpose xn. Okay. Good. So this is called cross entropy error. It's very important, yeah. If you have got lost a little bit in the details of the derivation or something like this, just know that logistic regression minimizes what is called cross entropy error. It's a very important error function, yeah. And this error is really similar to like mean squared error, another error function that you see in machine learning, yeah. And it really depends on every example. So it depends, right, on the values of the weights, the current weights, right? The value of the feature, the label, yeah. So, okay. So I'll start again so please log in again. I'll start the meeting and log in again. Yes, error function is the same as the loss function. It's the same, just different terminologies. Okay. So I'm waiting for it to end. It says less than a minute.
Do you want us to leave and come back now? Or,
yeah, well, I'm waiting for it to end. I don't know why. Maybe it will not.
You can end the meeting. You can force end it by doing leave meeting.
Should I end it now? Better?
Yeah, end it now.
Yeah.